Today I want to look at a problem that I've had for a while with designing Eurorack instruments and ancillaries, and that is how to turn a trigger pulse into a gate. Seemingly a very simple issue, but try as I might, I found very little online as to how to do this as a DIY hobbyist. So I turned to my Bible on this sort of issue, which is the CMOS Cookbook by Dan Lancaster. If you don't have this book and you're into this sort of DIY hacking, I cannot recommend it strongly enough. And let's turn to a page on this chip here, which is called CD4047 multi-vibrator. Quite an old chip now. You'll not find it used much in modern applications. Most of this is done by computers these days. But for our purposes, it's going to do very well. So CD4047, a multi-vibrator, it can be either monostable or it can be astable. We're going to look at it in a monostable situation here. So as a monostable, the circuit can be triggered by either a positive or negative trigger pulse, and there are different inputs for that, so that's good. We can put a pulse input from our Eurorack into the chip, and what this chip is going to do is effectively turn it into either a shorter or a longer pulse, so for our purposes a gate. So the output pulse width is determined by an external resistor and capacitor. We'll talk about the curves of that in a moment. The resistor will vary from 10k to 1 megaohm, so we can vary that using a potentiometer. And capacitance from very small upwards. And it's the capacitance that determines the range of the pulse width for a selected resistance. And there are also complementary outputs. All that means is that there's both a positive output and a negative output, again on separate pins of the chip. So let's have a look now a bit further on in the book, and we have some explanation of what that actually means in practice. So we're going to be looking at this top diagram here, which is for a positively triggered. So we can see the input coming in on pin 8. There's a variety of connections to both positive voltage, so VCC, in our case it can be 5 volts, and then some pins which are tied to ground to make the chip work. The outputs are on pins 10 and 11, 10 for a positive and 11 for a negative, and then pins 1, 2 and 3, this is where this resistive capacitive sort of network are attached into the chip, and depending on the values of these we get a different output on pins 10 and 11, as in a different pulse width output. And the pulses here will be at VCC, so if we put 5 volts on VCC we're going to get near enough a 5 volt output, or we should do. So let's flip the page, and this then is the graph of on time versus resistance and capacitance. So we have capacitance on the left here, and we have resistance on the x-axis. And then we have these curves which are plotted for that resistance. I beg your pardon, resistance isn't on this axis, this is the time, and then these are the resistance curves for different resistance. So if, for example, we were to put a 0.1 capacitance value for, let's say, 1 mega ohm, we would expect somewhere around 600 milliseconds of time delay. In other words, the pulse width would be somewhere around 600 milliseconds. That's a bit short for us, so we're actually going to go up to 1 microfarad as our capacitance, and we're going to use a 1 mega ohm potentiometer, and that will allow us to sweep along this line for the values of the pulse width we're going to get. So at very low values we can expect, very short pulses, sub 10 milliseconds. And for 1 mega ohm we can expect a pulse width or a gate output of somewhere, I don't know, 5, 6, 7 seconds. So that's a nice long spread that we can use for that value of capacitance. Okay, so let's have a look at this then on the breadboard. So here's our circuit all up. So I have a pulse coming in from my pulse generator into the system through the chip. Here's my 1 microfarad capacitor, and then I've wired in a 1 mega ohm potentiometer here. So let's have a look at the oscilloscope then. I'll turn some power on and we'll turn the pulse generator on. So here's our 5-volt pulse coming out of the pulse generator, and that's got a pulse width of about 2.5 microseconds. So I've turned the potentiometer right down. So let's now have a look at the trace for that. And here's our trace. They're not overlaid, so I've put the channel 2 down a little bit in terms of its position so that we can see the difference. So you can see that the pulse actually that's coming out, if I expand that a bit and I don't lose it, you can see it's actually shorter than the pulse that we put in. So let's bring that out again, put it over here, and we'll just start to increase the resistance on the potentiometer. And we should see, oh, that's quite touchy. Let's push this out a bit more. And you can see now that we can get a 5-volt pulse output or gate output from that short input pulse. And we can vary that using the potentiometer. It's touchy because we're actually at very short pulse width still here at the moment, in the order of what, this is 200 milliseconds. So let's try and expand that out a bit. Now bearing in mind that because we're going to expand it out a bit, we've got the update rate of the scope to deal with, and we'll slow down our input pulse down to 1 hertz. See if we can trigger as far over as we can. So here's our input pulse in yellow, our gate coming out, and I'm just going to start to very gently increase this potentiometer. You can see now that we can vary the output or the gate that we're deriving from that short pulse. So we're up at about a second now. Now one thing that this chip will not do is re-trigger. Now whether or not you think that's a good or a bad thing is down to the way you're going to use this. But if I put a suitably long gate in, as we've got now, you can see that it's not going to re-trigger on every pulse. It waits until its output has gone low before it will accept a new trigger. So that's going to be just a limitation of the system that we're going to implement. Okay, so I hope you found that useful. Again, the Bible, CMOS Cookbook by Dan Lancaster. A great book if you're into this sort of hacking. And the CD4047, this is going to be a very useful circuit when we come to look at the wider project of designing a synthesizer based on those big function generators, those big oscillators that we're repairing, the Marconi TF1101s, and there's videos on that on the channel if you're interested. So I hope you found that useful. Thank you very much for watching.